Hi, my name is Evan Wen, and today I'll be talking about relax. So, optical coherence tomography, or OCT, is a non-invasive imaging test for cross-sectional slices of a patient's retina. OCT imaging is used to diagnose several types of retinal disease. This is important because 1,100 million are affected by vision impairment, and it is estimated over 90% of these cases are preventable or treatable. So researchers have attempted to use deep learning to classify OCT scans. However, deep learning has a black box scheme in that there is no interpretability. As a result, heat maps have been used to give some sort of explanation. Heat maps are very coarse in general, and they're not very specific. Thus, non-ophthalmologists will have a lot of difficulty understanding them. For our work, we wanted to develop a novel CNN-based architecture for accurate OCT classification. Next, we wanted to localize the model's focus in the input image's pixel space, and finally, we wanted to retrieve qualitative and quantitative breakdowns of the model's focus. We used the Kermani OCT dataset, which contains around 84,000 images of CNV, DME, drusen, and normal varieties. For our CNN architecture, we use an efficient net V2 backbone with a linear head. We train with Atom Optimizer 0.001 learning rate, categorical cross entropy, 20 epochs, and a batch size of 64. On the right here, we can see our class weighting procedure. Here are the results from our model. As we obtained 99.8% accuracy. As we can see here, we beat all previous works, thus giving a new state-of-art result. To achieve better explanations, we use retinal layer attribution. Essentially, we seek to determine how much that each retinal layer contributes to the classification. To do this, we take the sum of the heat map values of all pixels for a given retinal layer and divide by the total sum of heat map values. This gives us the average model focus for correct classifications, essentially how much each retinal layer is involved in each classification. So for these three layers here, CNV prioritizes them the most. And then if we look at this layer, DME prioritizes it the most. Same with this layer, these two layers in drusen, and this one in normal. Here we show that these values are normally distributed. Essentially, you're most likely to get a value in the mean, and as you go further away, the chance of that being the value in a correct classification is much lower. And if we look at an incorrect classification here, we can see that these four layers have very significant deviation, making this prediction very statistically suspicious.